This is lecture 28 and we were discussing turbulent premix flames. So, yesterday we had very little time to really take the discussion far. So, we will start almost from where we ended yesterday, and we were discussing turbulent premix flames in a simple situation. Let us say there is a tube, and then if you send a fuel air mixture through it, and that is at a high enough velocity, and the flow has some disturbance. So, you have turbulent flow, and if you set up a flame on this, the flame that you get is a turbulent premix flames, because the fuel and air are mixed prior to leaving the burner, and it is also giving a flame which is turbulent, which is set up in a turbulent flow field. So, it is a turbulent premix flame. And what we understood through discussion as well as looking at one of the videos is that if you just look at it, or if you take pictures with less number of frames per second, then you will be able to see essentially a thick flame. Okay. And that thick flame has a name, it is called a turbulent flame brush. But we also understood through discussion yesterday that if you are able to take an instantaneous picture of the flame, instantaneous picture, and you can do that using appropriate optical method and high camera speed. So, you will be able to get, you will be able to see flames like this maybe. And we got some idea of this when we looked at the high frame speed images of a turbulent premix flame, and we had a sense that that flame is like more like this flame which is oscillating, which is moving about. So, an instantaneous image actually does not give you the appearance of a thick flame, which shows you more like a thin flame, if you are able to see an instantaneous image. Okay. So, this is what I am drawing, and we could not see that clearly in the 300 fps image yesterday, but you could sense that it is something like this which is moving about. Now, this instantaneous image keeps on moving about, keeps on shifting, oscillating, fluctuating, and then you have multiple of those, and they together means when you superimpose these instantaneous images one over the other, then you should be able to get a flame like this turbulent flame brush. So, the instantaneous flame, if you are able to resolve that, it is actually thin and it is also highly convoluted, thin and highly convoluted. Convoluted means it has these folds which you can see. Okay. So, the thick flame which you saw, the turbulent flame brush, is actually a time averaged picture of the flame. So, with naked eye, that is what you get to see, because your eyes will not be able to sense the instantaneous images. And keeping this in mind, we understand that the instantaneous flame can be thin like a laminar flame. A laminar flame is thin, a laminar flame is not thick like the turbulent flame brush that you were seeing. So, laminar flame is thin and the instantaneous flame in the turbulent situation is also thin. So, that is why people say that the instantaneous thin flame is like a laminar flame. So, it is a laminar flamelet. So, the turbulent flame brush that you are getting is an assembly of many of these laminar flamelets. That is one way of looking at turbulent combustion. Okay. And this is what we essentially discussed yesterday, but the other thing that I also mentioned is that okay, there is, just as there is SL which is laminar burning velocity, there is also an S turbulent. SL is a property of the mixture. But this is not a property of the mixture. ST is not a property of the mixture. In fact, ST is hard to deal with. So, you can define ST as maybe m dot divided by A bar rho u rho u A bar. Now, what is A bar? A bar is some kind of an average out area, difficult to define, but ST is such that if you get some estimate of A bar, then A bar multiplied by ST multiplied by rho u will give you m dot, which is the mass consumption rate of the fuel air mixture. So, this is similar to what you write for laminar flames. For laminar flames also you write area into rho u into SL. So, that gives you the mass burning rate. So, you do same thing here. Only thing is that we understand that in a flame which is doing like this and which has this thick flame brush appearance, which one is A bar, this is a matter of some controversy. Okay. So, if you have, if the flame is between these two, maybe somewhere here you can define an A bar, okay. Or let us say there is a square duct or rectangular duct, I do not mean square. Suppose there is a duct with this rectangular opening and you got a flame which kind of looks like this, then maybe this can be approximated as something like this, like more straight edges, very approximate, somewhat controversial, but this is how we can get this A bar. And once we get that A bar, if we measure m dot, then knowing this unburnt gas density, we can get ST. So, that can be one way of getting ST, turbulent burning velocity. Why is turbulent burning velocity not a property of the mixture? Because it depends on the flow, because it depends on the turbulence levels in the flow. It depends on the fluid mechanics. Whereas, as long as the flow is laminar, whichever flame configuration that you get, laminar burning velocity is a property of the mixture. Adiabatic laminar burning velocity is actually a property of the mixture. Now, we will today try to understand some aspects of turbulent combustion. Remember what I said yesterday, that we can't start from first principles and do analysis and find expressions for turbulent burning velocity and find many details about turbulent flames. We will not be able to do that because of the inherent complications of this sort of a situation. So, the laminar flame study was done more analytically. Here this will be more phenomenological and empirical. Okay. So, in this context, let us just see how to proceed. We can try to actually define some flow, some regimes of turbulent combustion. So, there can be some regimes of turbulent premixed flames. Some regimes of turbulent premixed flames, and to define those, we need to use, first we will talk about some length scales. Again, you may not be familiar with this, and we do not have sufficient time to discuss turbulent length scales, turbulent flow fields, but we will accept at some level and then probably keep going back to these issues and also read up the necessary chapters from the book, so that we develop our understanding over a period of time. Now, some length scales we need are Lk, which is associated with the smallest AD size in a turbulent flow field. Okay. So, this is called a Kolmogorov length scale. So, this corresponds to the smallest AD sizes. So, what are ADs? ADs are like fluid packets which are rotating, turning, which have vorticity. Okay. So, the smallest AD sizes correspond to this Kolmogorov length scale. And we also have LO, which is the other extreme, which is the integral length scale, or turbulence macro scale. Okay. So, this physically represents the mean size of large ADs in a turbulent flow. Physically represents the mean size of large ADs in a turbulent flow. So, Lk is like a small thing, it represents the smallest AD sizes, and LO is the integral length scales which corresponds to larger radius. So, these two are important length scales in our discussion. The other length scale which will be important for us is delta L, which is flame thickness, but you might have guessed because I am writing delta L here, L subscript. So, this is a laminar flame thickness. So, we do not know that much about LK and LO. We do not know how to calculate LK and LO. I mean, we have not discussed LK and LO in this course. In some other course, you may have seen that. Yeah.
Delta L is length scale.
Delta is a length scale because it is a thickness. So, it is a thickness of a laminar flame. So, suppose you have a propane air mixture. For that, you can calculate laminar burning velocity, you can calculate delta L, right. So, that delta L is a length scale because it's actually a length, right. So, these are three important length scales. Now, you may be wondering why we are talking about laminar flame thickness when we are actually discussing turbulent premix combustion. The reason is this, that the instantaneous flame is kind of like a laminar thin flame, okay, which is now in a turbulent flow field. So, we can think of a turbulent premix flames at least in some limits when you have a laminar flame which is greatly affected by the turbulence in the flow. Okay. So, that is why the laminar flame thickness is important. The other reason why laminar flame thickness is important is that it is some kind of a length scale pertaining to the flame, that LK and LO are length scales pertaining to the flow field, and this is a length scale which pertains to the flame. And this length scale is for a laminar flame situation. So, it also connects to molecular processes in the flame. So, what I mean by that is that you get the laminar flame thickness based on chemical reactions, based on processes like mass diffusion and heat conduction. These are actually molecular level processes. These are not affected by these are not essentially turbulent processes. Okay. So, if you have studied little bit of turbulence, maybe in the previous semesters also you started looking at it in the convective heat and mass transfer course, then the reason turbulent transport processes are more effective than laminar transport processes is that the diffusivity increases significantly. Okay. So, there is a molecular diffusivity, but there is also turbulent diffusivity. So, the turbulent diffusivity is actually much higher than molecular diffusivity because of these all these rotating ADs and better mixing processes and things like that. Okay. So, what I am telling you right now is rather a simple description of things, but the fact remains that in a turbulent flame we can think of laminar flame thickness as a possible length scale. Okay. So, that gives us something about the flame length scale, and then we have LK and LO representing the turbulent flow field. Now, in a turbulent flow field there are various length scales possible, not just the lowest of those length scales which is the Kolmogorov length scale, or the highest of the length scales which is the integral length scales. There may be intermediate length scales also, but LK and LO are like the two extremes. Now, depending on this LK, LO and delta L, three regimes of turbulent premix flames can be defined. So, people have defined these three. So, we have, let us say, wrinkled laminar flames is the first one. In wrinkled laminar flames, delta L is less or equal to LK. So, the laminar flame thickness is smaller than even the smallest of the turbulent length scales. Now, number 2 is called flamelets in eddies, and that is LO less than LO greater than delta L and delta L greater than LK. And then there is a distributed reaction regime where delta L is greater than LO. So, quite obvious. Delta L can be very small if it is smaller than, it is so small that it is smaller than even the Kolmogorov length scale. So, if it is like that, then we call it a wrinkled laminar flame. So, that is a wrinkled laminar flame when laminar flame thickness is small compared to even the smallest of the turbulent flow scales. And on the other extreme, we have distributed reaction zone, where delta L is even more than the largest of the turbulent length scales. So, delta L greater than LO is the distributed reaction regime. Now, there is an intermediate regime which is called flamelet in eddies. Okay. Now, today our purpose will be to try and understand something about these regimes. So, we will do that by looking at a plot. So, this is a regime diagram, and okay, so we got something like this, and in case you are not able to read the x axis is turbulence Reynolds number, Reynolds number. So, the turbulence Reynolds number is V prime RMS into LO divided by nu. Okay. Maybe what I can do is I can shift this a little bit and write V prime RMS LO by nu. All right. So, this is what I mean. This is on the x axis. Okay. All right. Now, this is a plot which helps us understand the various regimes of turbulence, the turbulent premix combustion. Now, there are various lines on the plot, and before we go to the lines, let us see what do we have on the x axis and y axis. X axis I told you turbulence Reynolds number, which is V prime RMS LO divided by nu. Now, what is LO? Integral length scale. What is nu? Nu is a, what do you think nu is? Kinematic viscosity. Okay. And V prime RMS, are you familiar with this? Root mean square of the fluctuations in velocity. Okay. So, this is a representative quantity of the fluctuations. So, you know what is the root mean square. Right? So, you have the fluctuations, you take the squares and you take the mean of those squares and you take a root of the mean of those squares, then you get the root mean square. So, this is representing turbulent fluctuations. So, V prime RMS into LO by nu is what you have on the x axis. On the y axis, you have Darm-Kohler number. Now, that is a new quantity. So, just in a minute we will come back to this plot, but let me just explain what is a Darm-Kohler number. So, the Darm-Kohler number is an important quantity in combustion. And this is written as a dA, sometimes it is written with just a d, and this is essentially a flow time divided by a chemical time. Flow time divided by a chemical time. So, how will we write a flow time? We will write flow time in this context as LO divided by V prime RMS. So, is LO divided by V prime RMS a time scale? It is, right, because this is a length scale divided by a velocity. So, this will give you a time. So, this is a flow time. LO divided by V prime RMS is a flow time. It is kind of like the lifetime of large eddies in a turbulent flow. Now, tau chemical is delta L divided by SL. So, this is a chemical time scale, and this we are getting using the laminar flame thickness and the laminar burning velocity. It somehow brings in chemistry, because there is chemistry hidden inside this SL as well as in delta. Okay. Now, again check whether it has a time scale. Obviously, it has, because this is length scale divided by a velocity scale. So, this is also time. So, this is Damkohler number. Now, what does a high Damkohler number mean? For example, suppose we say the Damkohler number is much greater than 1, what does it mean? That the chemical reaction time scale is very small compared to the flow time scale. Okay. So, this is like a fast chemistry regime. And if Damkohler number is not so high, then the chemistry is not fast, and the Damkohler number, if the Damkohler number is small, it is more like a slow chemistry regime. Okay. Because in that case, the chemical time scale is large compared to the flow time scale, and then Damkohler number will turn out to be small. So, this is one thing which we have to remember. So, the plot that we were seeing is an important plot, because it's wide, this sort of plots are widely used in combustion literature. Okay. So, now that we understand the two axes, let us look at what lines we have. So, there are two major lines. Actually, you see a bold line here, and you see another bold line here, and this bold line says Lk by delta L equal to 1. So, on this line, the Kolmogorov length scale divided by the flame thickness is equal to 1. And on this line, you have LO by delta L equal to 1. Okay. So, that means the integral length scale divided by the flame thickness is equal to 1. You also see that different regimes are marked. For example, you have A, which is above this solid line. So, above this solid line, what happens? You get reaction sheets. By reaction, it is written reaction sheets in this particular plot, but actually what is meant is that it is a wrinkle reaction sheet regime. Okay. What was the wrinkle reaction sheet regime? Wrinkle reaction sheet regime was delta L less than Lk, isn't it? Delta L is less than Lk. So, Lk by delta L is in fact greater than 1. So, what that means is, if you go above this line, you go to a situation where Lk by delta L is greater than 1. That means delta L is small compared to Lk, which is the reaction sheet regime. So, that is we wrote 3 regimes, this is the first one. So, this is a wrinkle reaction sheet regime. And what was the other extreme? We said that delta L is in fact even more than the integral length scale. Okay. Sometime back we said that. So, that is the distributed reaction regime here. So, in this zone, this is C. In this zone, delta L is in fact more than LO. So, LO by delta L is less than 1. So, that is how you reach here. Then there was this intermediate regime which we called flamelet in eddies. So, that is between these two lines. So, above this line is wrinkle reaction sheet, and here below this line is distributed reactions, and between these two solid lines is flamelet in eddies. So, we understand that much, but we also see that the regimes depend on the Damkohler number and also the turbulence Reynolds number. Okay. See, it's mechanically we can understand that, okay, this is Lk by delta L, so above that is the wrinkled reaction sheet, right. But we also understand, if we observe closely, we also understand that we get wrinkled reaction sheets if the Damkohler number is high. So, we define the regime saying that delta L less than Lk is wrinkled reaction sheet, but this particular plot is also giving us some extra information. It is telling us that the Damkohler number has to be high to get wrinkled reaction sheet, correct. So, that means the chemistry has to be fast. So, a fast chemistry is likely to give you, more likely to give you a reaction sheet regime. Okay. So, can we somehow interpret this? Is it possible to relate to this somehow? High Damkohler number means fast chemistry, and why is it that fast chemistry is likely to give you reaction sheets?
What do you mean by wrinkled laminar flames?
Yeah, so we haven't discussed the physical aspects of it, but as of now, what do we know about these wrinkled reaction sheets? We know that the flame thickness is actually smaller than even the smallest length scale in the turbulent flow field, right. So, keeping that in mind, can we say that high Damkohler number is likely to give us wrinkled reaction sheets? Fast reaction rate, high Damkohler number is fast chemistry, and if there is fast chemistry, then the flame thickness will be smaller. If the flame thickness is smaller, then you are more likely to get wrinkled reaction sheets. Okay, this much we understand now, right. But of course, we physically haven't discussed this so much so far, but we will go to that. Now, using that sort of discussion, using a similar sort of discussion, can we look at the distributed reaction regime and say why the distributed reaction regime is for low Damkohler number? Same argument, isn't it? So, you will see that C regime on the plot, which is for low Damkohler number less than 1, small Damkohler number. For small Damkohler number, we are not getting fast chemistry regime. So, we expect the flame thickness to be large, and if the flame thickness is large, probably it is even larger than LO. Okay. Then you get distributed reaction regime, and in between you get B, which is flamelet in eddies. So, we understand that Damkohler number is playing a role. Okay. Is the turbulence Reynolds number also playing a role? Yeah, because it is also the all regimes are also function of the turbulence Reynolds number also. So, there is an interaction between the flow turbulence as well as the chemistry. The chemistry is coming through that chemical time scale, which is in the Damkohler number. Okay, so we have some understanding now, but let us also think about the wrinkled reaction sheet regime to some extent. Now, if you have, for example, a thin flame, which is a laminar kind of flame, okay, and reaction is fast, so it is a thin flame, but now you put in turbulence, then what turbulence does is the turbulence makes the flame wrinkled. Okay. So, we like to think of wrinkled reaction sheet regime as a regime when the flame is inherently thin, but the turbulence is disturbing the flame by actually making it corrugated, bringing all these folds, these convolutions in the structure. So, all that the turbulence is being able to do is to make the flame corrugated, make the flame wrinkled. Fine. Turbulence has some effect on combustion, but the effect on combustion that turbulence has comes mainly through the wrinkling of the flame and the increased area, okay, in this regime. So, what else turbulence can do? If turbulence can enter the flame, then it can affect the processes in a flame. Okay? So, if there is a thick flame, suppose this is the flame thickness, suppose this is delta L, right. I am talking not about wrinkled reaction sheet regime now, but I am just talking about a general flame which has a thickness of delta L. Now, if the turbulence length scales are small compared to delta L, what will happen? That the ADs, the process, the turbulent fluctuations and the vorticity, they will affect the processes in the flame. They will affect how reaction takes place. They will have affect within the flame thickness, they will affect processes, right. They will affect the mixing of fuel and air. It will affect a lot of things. So, that is one kind of effect. So, that effect is more in the distributed reaction regime, that sort of thing, because then the flame thickness is large and then turbulence length scales are smaller. So, they can affect processes within the flame. Okay. Whereas, in the other case, if you have a thin flame, let us say this line is just the flame and the turbulence length scales are bigger, that is even the Kolmogorov length scale is bigger than this flame thickness. So, this flame thickness is this delta L. Even the Kolmogorov length scale is bigger than this. So, it cannot affect what is going on inside the flame. Okay. The fluctuations and the vorticity in the turbulent flow field cannot actually change anything very significantly within the thickness of the flame, because the turbulent processes are too large. But it can actually change this by twisting it. It can do that in a turbulent flow field. So, that is why if you get something like this, so it is more like this laminar flame which has been twisted around by turbulence. So, this is in the wrinkled reaction sheet regime.
This twisting is also possible for the thick, where the ADs are smaller.
Yeah, but there the all turbulence processes are actually within the delta, all processes. So, the main effect will be definitely all the turbulence processes affecting the inside of the flame.
That makes the reaction rate.
It will affect the reaction rate. No, it does not necessarily make the reaction rate small. Maybe the reaction rate is small, that is why delta L is large. Okay. See, here we are in this situation, we are saying that the delta L is large. Why is it large? Maybe because it's a fuel which is not very reactive, or maybe it is not even a combustion reaction. This is a reaction with something else, pollutant formation reactions. See, NOx formation reaction is, for example, is much slower than a hydrocarbon combustion reaction. So, this thickness, maybe it is some pollutant, it is not exactly a flame, or maybe this is for a fuel which is not reacting much. Yeah.
Can we interpret it like this? When the reaction rate is small, the heat generation will be less. Temperature gradient towards from flame to inward side will be less. So, flame would like to move towards the thickness will be high, because its reaction is less. So, it will try to have a more zone for generation of the heat and reaction purpose. That's why.
Yeah. So, there is a temperature, correct. So, the question is how does it relate, how does a large flame thickness relate to temperature? So, we kind of know this from previous experience, because we were doing this laminar flame speed, laminar burning velocity, and we understood that if the fuel is reacting fast, then the reaction zone is thin, then the reaction gets over over a small length, which we call the flame thickness, right. And reaction is getting over quickly, so the reaction zone temperature is also expected to be higher. Okay. Otherwise, see, the reaction rate is dependent on the temperatures. The reaction rate is definitely dependent on the temperature. Reaction rate is affected by temperature as well as fuel and oxidizer concentrations in the zone. So, it must be reacting well, releasing heat quickly over a small thickness, that is why temperatures are high. Okay. coming back to this wrinkled reaction sheet. So, the fact that we are calling it a reaction sheet means that the word sheet, of course, it means that it is thin, otherwise we would not have called it a sheet. So, from the name you can understand that this is a sheet. So, this is thin and it is a wrinkled reaction sheet. So, this must be the situation, this must be the regime where turbulence cannot affect processes within the flame, but being able to affect processes, able to affect the flame by twisting it, actually by making it convoluted, by giving it wrinkles. Okay. So, this is the wrinkled reaction sheet regime. This wrinkled reaction sheet regime is actually very important from practical combustion point of view. In fact, we will go back to the plot. We will go back to the plot. So, this is turbulence Reynolds number, this is Darm-Kohler number. Remember the regimes. We are now talking about regime A, which is wrinkled reaction sheet, and you will also notice that there is a square box out there. Okay. That box is something which we haven't discussed so far. This box indicates the regime in which most engine combustion takes place. Okay. In fact, there are points, there are these diamonds, the squares, the triangles and the circles which you see. These are experimental data points for engine operation. So, these are practical points, and you will see that most of these points are actually in the wrinkled reaction sheet regime. So, in a spark ignition engine, for example, it is more like a wrinkled reaction sheet regime. Okay. So, from a practical point of view, it is in fact very important. We still haven't understood this plot so well. I mean, I don't know whether we can complete it today, but there are still some lines, some more lines, isn't it? There is this line here, and then there is V prime RMS divided by SL equal to 1, that line here. So, we have to be mindful about these things. Anyway, so this was a digression. We will go back to the wrinkled reaction sheet regime again, and we will try to write something for turbulent burning velocity in the wrinkled reaction sheet regime. Wrinkled reaction sheet regime is important from engine combustion point of view. It has a lot of practical importance. So, can we write, let us say, some expression for turbulent burning velocity? If we can write that, then the turbulent burning velocity can be related to mass consumption rate. So, that is something which will be useful for us. Now, as I said, we write m dot equal to rho u a bar into St. Rho u a bar into St, and I told you the problem regarding this. It is hard to get St from velocity measurements. We could have got St from velocity measurements. St is a burning velocity, and we said burning velocity is the gas flow velocity into the flame, right, normal to the flame. Okay. But measuring that is very hard in a turbulent flame situation. So, that is kind of ruled out. So, what we typically think of doing is that we will get some information about A bar, okay, maybe from flame images, maybe we will try to have some kind of an estimate for A bar. This is also not easy, but it is easier than measuring velocities. So, we can get A bar, and then getting m dot may not be such a big problem. If you are doing an experiment, you are sending some m dot through a tube, and you can get that m dot. Okay. So, if you get that, rho u is easy. In fact, it is the easiest, and from that you can get St. St we are calling a turbulent burning velocity. Let us also appreciate one fact, that turbulent burning velocity is typically much larger than laminar burning velocity. Laminar burning velocity is of the order of a few centimeters per second, correct? (40, 50, 60 centimeters per second). High for some other fuels, maybe hydrogen, but turbulent burning velocity can be of the order of several meters per second quite easily. Okay. So, that means in a turbulent flow field, the burning velocity increases significantly. So, it can be 2 orders of magnitude almost higher than this. Somewhere I read it can be 5 to 50 times higher than laminar burning velocity. Maybe 100 times also, I am not very sure, but okay, let us stick to 5 to 50. Yeah, typical situations. We are mostly talking about hydrocarbons. So, it is much larger. ST is higher. ST is higher than basically SL. This is laminar burning velocity, LBV. So, that is good, actually that is good, because if you have a burning velocity which is really high, then that is good for industrial applications, that is good for engines. If you try to run an engine, so let us say a spark ignition engine which employs laminar combustion, then you will have a very hard time because the burning rates are low. So, turbulence increases the burning rates, and that is because we can understand to some extent now that okay, you have this laminar flames, essentially laminar flamelets, which have been, because of turbulence, which have been made different. The area has changed, they have become wrinkled. Okay. So, there is an increase in area, and there will be an increase in laminar burning velocity. So, if you there is an increase in burning velocity, so turbulent burning velocity will be much higher than laminar burning velocity. So, people tried to calculate this, and one of the first models for this calculation was given by Damkohler himself. So, he said, he postulated that ST is ST, the turbulent burning velocity is 1 plus A wrinkles, area of just the wrinkles. Okay, so, there is an average area plus you add the area of the wrinkles, you get the total flame area. So, it is A wrinkles divided by A bar into SL. Okay, that is what he said, and he also said that this is equal to 1 plus V prime RMS divided by SL into SL. So, ST is this. So, this is kind of empirical. Okay. All right. So, this is what I was telling you about, that this is not based on some theory which you do from first principles and do lots of derivations, lots of experiments, lots of data, not that sort of thing. Of course, there are experiments, and based on experiments and data, he could arrive at something like this. He had some justification based on the data that he collected. Okay. And now we see that there was value in determining laminar burning velocity also. We determined SL, which was the laminar burning velocity. We have expression for this, we have correlations for this, we have measurements for this for various kinds of hydrocarbons. So, if somebody tells you that laminar burning velocity is important only in laminar flow situation, that is not exactly correct. That is not correct, because even when the flow situation is turbulent, the turbulent burning velocity can be calculated with the help of laminar burning velocity. Okay. And what else would you need? You need V prime RMS, and that is it, V prime RMS divided by SL into here, and then SL outside this. So, who will give you V prime RMS? Maybe you have to measure it, or in some engine applications there are some correlations which give you V prime RMS in terms of the engine speed and things like that. Okay. So, this can come from correlations or from measurements. So, you can get V prime RMS, and then you get turbulent burning velocity. You can see from here that even though SL is a property of the mixture, ST will depend on V prime RMS. That is, so one situation you have some V prime RMS, this will give you some value of ST, you change V prime RMS, then the ST value will change. So, it is not a fundamental property. So, it depends on the fluid mechanics of the situation. So, this is the Damkohler model, and this model was given in I think 1940, yes, 1940, long time back. And then these subsequently there have been some other people giving models, and these are all again all empirical models. So, there is a second model. So, Damkohler is first, so we can call it number 1, and then there is a Clavin and Williams model, which is 1982, and then that gave ST by SL 0.5. CLAVIN, the Clavin. Okay. And this is Williams. And actually C is approximately equal to 1, very close to 1. Yeah.
In the previous equation, how do we get this A wrinkles divided by A bar is equal to V prime RMS by SL?
Yeah, so it's again not. So the question is why? How do we write A wrinkles divided by A bar as V prime RMS by SL? This is based on experimental data. This is more of a hypothesis that he verified with the help of experimental data.
Nothing to do with the equivalence of mass flow rate in the two conditions and then.
No, not exactly at least. Yeah, so that would have. Yeah, so actually that's a good question. In fact, this the mean he wrote this A bar going with SL, okay, as which is the average area going with SL, and the wrinkles going with the fluctuations. Okay, the wrinkles going with the fluctuation and the main area going with laminar burning velocity. So this seems to make some kind of a.
So it is rather quite reverse. This
Yeah.
A bar is going with V bar RMS and SL going with A wrinkles. So that
okay, in terms of mass flow rate, exactly. Yeah. Yeah, there is actually he didn't directly use he didn't use a mass balance or something to get this. This is more of a postulate. Okay. Actually, if since you asked this question, let me also write this. See, m dot is rho u A bar ST, and he wrote this as rho u A flamelets into SL, okay, and he wrote A flamelets is equal to A bar plus A wrinkles, okay. Using this and this, you can get this. Think about this one. Here, using these two, you can get ST by SL as A flamelets divided by A bar. ST by SL is A flamelets divided by A bar, and A flamelets is A bar plus A wrinkles. If you take that, then you will get this, and then from here to here, it's an assumption.
Can we take ST as V prime RMS?
ST we cannot take as V prime RMS. ST is something for which we are trying to find an expression, and we cannot do that because ST is connected more with the flame, whereas V prime RMS exists in the flow field.
That's the reason, because in the laminar flow, SL was related to flow. The SL, the laminar speed was just equal to the way the unburnt mixture was moving towards the flow. So we equated that. So similarly, the V RMS prime, which is equivalent to the mean flow rate of the unburnt mixture, and that can be related to the this turbulent.
Actually, V prime RMS is not the mean flow rate. No, this is the fluctuation over the mean. Fluctuation over the mean. Only the fluctuation. It's some kind of a mean fluctuation. This is actually not the mean fluctuation. Mean of the. Okay, you take the squares and take the mean, then take a root of that. Okay. So the basic justification for what you just now saw is from here, that he wrote rho u A bar ST as the mass consumption rate, and he wrote that equal to rho u A flamelets. A flamelets is what? A flamelets is more like this thing, okay, and A bar is more like this, and the difference between the two is actually wrinkles. So, this is more of a postulate that the wrinkles divided by A bar will go with V prime RMS divided by SL. Okay, the balance, I think your initial question, if I understood it correctly, was more in terms of mass balances. The mass balance is actually the one which he used is this. Okay, but maybe see, it's like you can think of this as, okay, it's easy to remember in the sense that wrinkles will go with RMS because of the fluctuation part, and the mean area will go with the laminar burning velocity. So, that is an easy way to remember this. But he postulated this, and then he had experiments, so he could finally arrive at this. This is 1940. This is the first model, and the first models are usually remembered, so that is why it is not a bad thing to do. And then we have this one, which is Clavin and Williams model, and there is also Klimov model, which is ST by SL equal to 3.5 V prime RMS divided by SL to the power 0.7 for again, no need to remember these things, but you should know that such relations exist, so that you can use these if necessary. And there are many other models available, and the general agreement is that ST by SL depends primarily on V prime RMS by SL. Okay. In all the models, the sort of thing which people are agreeing on is ST by SL depends on V prime RMS by SL, and does not involve any other turbulence properties such as length scales. Now, we can see that ST by SL in the Damkohler model goes with V prime RMS by SL, and here also it is V prime RMS by SL squared. Here it is V prime RMS by SL to the power 0.7. This is all empirical, so you can see that there is a lot of variation in the models which use. There are other models also. These three are not the only three models. Okay, so we ran out of time today, and tomorrow we will discuss a little bit about the other regimes. The other regimes will not take us that much amount of time. There is flamelet in eddies, and there is distributed reaction zone. This is the most important regime from engine point of view, from lot of practical combustion devices point of view. Remember that box that we saw in the regime diagram. Okay, so we'll stop here. We'll meet tomorrow.